Hello, finally. Today I'll be talking about some methods of probing quantum magnetic systems, and I'll mostly be focusing on the optics part. In the spirit of time, I'll try to be a little bit quicker. So, just to give a picture which everyone understands, what are the kind of aims which one want to look at when, if you want to experimentally probe anything quantum about a magnon? Well, you want to, I guess you want to start with some kind of a state, and you want to be able to generate a quantum state and then be able to measure it, right? So there are two basic steps which one needs to understand. What I'll be talking about today is purely the measurement part. And this is a introduction which Akash and Sylvia has talked a lot about already, but I mean it makes no sense to talk about quantum magnets without knowing if magnets are even quantum to begin with. And let this be a bit of a reminder from yesterday's talks that there is this amazing experiments by Nakamura group where they coupled a ferromagnet to a superconducting qubit via a microwave cavity. What they observed was the susceptibility of the qubit, as you can see on the right side, shows some peaks behavior, and that peak behavior is kind of an evidence for the fact that magnons are quantized. If they were not quantized, it would be a continuous distribution going down. I'm also pointing this out because just remember that this is kind of something similar I want to do with skyrmions to be able to somehow find a way to get an evidence for the quantization of energy levels in a system, and this is done for magnons. This is kind of in the exact same setup as I showed before. This, as Akash and Sylvia again has pointed out before, that there were experiments where they were able to see non-classical states of magnons. So just a reminder again, sorry, in the bottom you can see what they expect if they create the state upwards. For instance, for a First Fock state, you should have something like a negative blob in between a top block of the Wigner function, and what they observe is pretty much the same thing. Now, part of the question comes in, I'm going to talk about optics, and all the previous two amazing experiments I showed were superconducting qubits. So the question is, if the qubits are so awesome, then why do we care about any other way to measure magnon at all, right? And now I want to point a little bit about things which are, let's say, more on the horizon as to, yes, superconducting qubits are extremely sensitive. This is one of the best aspects of why they are used to measure any magnon properties. But they are always going to have problems with scalability, partially because of the microwave cavity which comes along with the transmitter, which you cannot get rid of so easily. And also, if you couple a transmitter to a magnet, you always induce additional dissipation, which is because they're always coupled, essentially always coupled, so you cannot get rid of them. With light, you kind of lose a lot of sensitivity. So I'm calling it moderate sensitivity, but that is being generous. However, you get a lot of other advantages. So one aspect is that light gives you a lot more spatial resolution, right? Because light can go down to half a micron or even smaller depending on the wavelength. So it allows you to work with magnons with much shorter wavelengths and a much broader set of magnetic systems, for instance. The third aspect, which I think is quite interesting for quantum information in particular, is the fact that the coupling to light is controllable. So if you shine a laser on a magnet, the coupling is on. If you don't have any laser, the coupling is off. So because of that, there is no dissipation outside the sort of measurement or the coupling window which you are interested in. And that's pretty important for preserving quantum information in any system, magnons or otherwise. So here's the motivation. Now, if the main problem with light is sensitivity, so let's at least try to quantify it theoretically as to how bad or how good it is, right? So the idea, to find out the theoretical limit to what you can do with light, I just start with the waveguide, a magnetic waveguide. I consider a case of a coherent laser coming in, and there is an output which is in the opposite polarization. You don't have to worry about all the details of the polarization or like things, but the main point is there is a laser coming in and there's an output, and the output can be measured, of course. A critical aspect of how much output is coming in is something I've written here, where A out is the annihilation operator for the output photons. A noise is an operator for all the noise sources. It could be from the vacuum fluctuations of electromagnetism or just the impurities in the magnet. An M signal is the annihilation operator for the magnon, which is the signal you want to discover. Obviously, if theta is high, then we have good signal. If theta is low, then we have a terrible signal to noise ratio. And what does theta depend on? So theta depends on a couple of things. First term here, which I'm calling coupling, is just a material parameter. It can vary widely across, going from yttrium to gadolinium or other things like that. It's something, it depends more precisely on the Faraday rotation or the Cotton-Mouton effect of the material. The second term is the vacuum fluctuations of spin. So if you have more fluctuations, then you create more photons and you have a stronger coupling to the photons. So that's something that's expected. The last term consists of some maybe terms which might look a little bit weird. It consists of specific heat, the density of the material, and the optical absorption. So the reason this term is there is because the way light magnon coupling works is that if you insert more laser, you get more coupling. So but then the question arises, can't you just input, I don't know, 1,000 watts and just get infinite signal? That is obviously not possible because it will lead to a significant heating of the sample. So focusing only on the sample aspect, a physical limit is given by the fact that the temperature rise because of laser should be limited, should be, let's say, 1/10 of the magnon frequency or something like that. So if you limit that, so this here is exactly the temperature rise in the material because of input laser. For YIG, this term turns out to be 0.2. It's kind of geometry independent or anything like that. And to compare this, the theoretical limit, which is purely material based, is like orders of magnitude more than what's experimentally observed. So of course there is a shitload of engineering required to actually reach this level, but this is kind of the aim, in some sense. Is there a point of looking at it? This kind of shows that there is a point of looking at it. Now, there is a number 0.2. What does it mean? Is it high? Is it low? So just as a simple example of what does this number 0.2 means in terms of how much quantum information you can extract. What I've plotted here is the first Wigner function is let's say somehow you manage to create a magnon state which is a superposition of the magnetization pointing in two different directions. So this Wigner function will look like that. What I'm plotting later is like, let's say if we somehow try to reconstruct the magnon density matrix based on only the optical data. So it's kind of a measure of how much information from magnons has been transferred into the optics. For a very low theta, what you can see is that the prediction, or let's say the information which actually optics encoded, are the peak positions. As you can see, it matches the original value. But there are no fringes in between, which translates to the fact that there is no that the photons do not see a quantum coherence of magnons. They just see the peak positions. Okay, maybe I want to go slightly quicker to the topic which I actually want to discuss in full detail here. Obviously, if you have any other questions about the previous part, I'll be happy to discuss in more detail. It was just for flashing some of the initial results I have. But this I'll talk less in more detail. What about optical signatures of quantum skyrmions? The point of this project was that there are kind of theories abound about how skyrmions show quantum behavior and how to treat them quantum mechanically. However, as far as we know, there is no experimental measurement of skyrmions behaving quantum mechanically at all. And of course, it's very hard because skyrmions are very small. It's very hard to probably measure the whole quantum state of the skyrmions. So what we want to look at here is, can we have some simpler witnesses which are let's say not dependent on doing a measurement super fast or having very high signals or something like that, but we can still tell you that skyrmion behaves quantum mechanically. So let me show you how. First, just a picture of skyrmion, which probably you have seen ample number of times, but it doesn't hurt to see it one more time, where there is a spin which is pointing down, and then it slowly goes into a ferromagnetic background which is pointing all the way up uniformly. Now, what happens in a frustrated magnet is that there is a there is a symmetry that if you rotate all spins by a constant angle, it does not change the energy. So naturally, you can start from something in the center, rotate it by pi by 2, and you will get a degenerate ground state. Not just pi by 2, you can rotate by any angle. So this angle of rotation, which is called helicity, which has been mentioned a couple of times by now. This helicity is a zero mode of skyrmion, and this is a quantum degree of freedom that I will be focusing on how to measure, how to see some quantum witness of this skyrmion helicity operator. To actually look at any observable, you have to couple to its conjugate momentum, right? That's the basic, not just quantum mechanics, classical mechanics rule as well. Now, this helicity is caused by rotating the magnetization, so it's probably not surprising to see that its conjugate momentum is just the total spin of the system, because that's a generator of rotation. This SZ here. It can be a total spin, you can restrict the volume around the skyrmion, but okay, you can take the whole volume as well, it doesn't really matter. But this SZ is what we want to couple to be able to measure helicity, anything about helicity. So to give you a basic idea of what the quantumness of the skyrmion shows up theoretically, this is work done by Christina and Christos, and then followed by many other works by Christina, where they derived a Hamiltonian for only the helicity degree of freedom. So this Hamiltonian is like ignoring all the other magnons, let's say. It's a relatively simple Hamiltonian. There's a quadratic term in SZ, which is like the momentum of helicity. There's subtraction of the ground state value, but that's not so relevant in the end. Then the first two parts are what would appear in any frustrated system. The third part is different because it's the potential for helicity. Now it's kind of contradictory to what I was saying before in some sense, and because I was saying that helicity is a zero mode, so the Hamiltonian should not depend on helicity. So this is the terms that appear only when you try to break the rotational symmetry. So it's a kind of way to control the potential of helicity to get something sensible out of the system. Typical case when, for instance, if you apply an electric field and if there is any polarization, any mechanism to generate polarization based on spin, would be something like the potential is cosine phi. So potential is not a very complex term, it's just a cosine phi term. And it's a relatively simple Hamiltonian. We can always find the eigenmodes, which will be the wave functions of the helicity and everything. So yeah, if we have the eigenmodes, now let's get back to the optical part of how do these eigenmodes couple to optics. So as I said, I want to see a quantum witness of this skyrmion. So to know what is quantum, you first have to know what's classical, otherwise it doesn't make any sense to compare. So let me first describe the classical skyrmion scattering. I'm just describing the features that I find after the calculation. So I'm not going to give you too many formulas. But yeah, the system essentially is a skyrmion, and there is light coming from the bottom with some polarization, as you can see. It's classical light, and the output will be in the opposite polarization. That's just the selection rule. And the major calculation that we'll do will be to calculate the spectrum of the output light. Okay. The theory of how light interacts with the spins is essentially that the spins or the magnetization, it doesn't really matter, that the spins affect the permittivity of the light in a way which is symmetry forbidden and all. The exact formula is not so important, but essentially yes, it affects how light moves through the magnet. Now if one performs these calculations and finds out the scattered light amplitude, it will just turn out to be a product of the input light and SZ, which was the total SZ, which is the conjugate momentum to helicity. So it's good that it's coupling to SZ so that it actually affects helicity degree of freedom. And I want to bring your attention to an important feature of this formula, which you can quite easily see, is the fact that the output scattered light is symmetric in sideband. So it's symmetric around the input frequency of the light. This does not always happen in magnons, because sometimes you have interference from Faraday effect in quantum motor. This does not always happen in weather magnons, but in this case, our system is symmetric enough that we have this frequency, this symmetry in your sidebands. This is important because this will be violated in quantum domain. And this is, so yeah, the fact that classically this symmetric is important for the next slide, which is now taking the exact same system. There's nothing changed in the system. The only thing we are doing is now analyzing the same system but quantum mechanically and seeing if something changes. Well, quantum mechanics is harder than classical physics, so this slide also has more equations than last slide. But yeah, this equation is relatively easy to understand, where A are the annihilation operators for photons, sigma are polarization, and k are wave vectors. What we are looking here is a scattering of light, because one light photon is annihilated, one is created, so one is absorbed, one is created, and scattered via the operator of Sz, again the total Z spin of the system. And the final result is also, maybe it's long, but it's actually probably easy to understand, as you can see, that the scattered output photons, its spectrum, is just proportional to the power spectral density of Sz. There's a Fourier transform of correlation function, right? Now, if you stare at it long enough, you will probably realize that if Sz at different times commute, then this frequency spectrum will be symmetric, because you can have this omega 2 minus omega. So the question of this frequency symmetry, it boils down to the question of does Sz at different times commute? Obviously, in a classical system, they will commute, so that's, we kind of recover the previous slide that yes, that the classical system will not show any side-band symmetry. Quantum system will almost always show it. I want to keep an eye out on the time. So now I apologize for one slide of theory just to explain like what kind of mechanisms are responsible to calculate this kind of a correlation function. Okay, you probably have seen something similar because it's just kind of a standard Lindblad equation where the first line is just the Heisenberg evolution. The second line consists of some operators where I put Sz, and there's an omega in between. Kind of ignore the omega for the time being. But this Sz operator is now acting as a dissipator for the density matrix of the skyrmion. If you look at it, same thing in an eigenstate picture, it's kind of like this Sz is going to excite all the transitions from ground all the way up. And the interesting thing is the kappa opt in front is constant for all transitions. So in some sense, it is acting like an infinite temperature bath, right? It does not care whether you come down or come up. It's just equal transitions. The last term is looks more complicated, but it's just one of the ways to represent thermal equilibrium. So if you don't have optical heating, we only have this last term thermalization, then the system will go back to the Gibbs distribution, which I pictographically shown here, like, okay, it's more probable to come down than to come up. So these are the two physical mechanisms, just the usual thermalization, which can be coming from all possible sources of dissipation. And there's optical heating, which is just coming from the extra laser that is exciting the skyrmions. Okay. Now to remind you, the main point that we were looking at was the asymmetry in the frequency, because that was the quantum feature. The question, so now this longest slide shows how big it is. I want to first draw attention to the plot directly. Here, kappa out is a measure of the probability, how many photons are generated by the skyrmion. So if we have a smaller kappa out, which basically means you have smaller laser power, so you have a smaller output as well, which also means you have smaller optical heating, so everything becomes smaller. And a higher number is exactly the opposite. At this value of kappa out, you can see that what I'm plotting is 0 here is just the input frequency. So you can clearly see there's a frequency sideband effect in the plot. Mathematically, where is it coming from? Where you have to kind of see at the top of the equation, which looks very long, but it's just a sum of Gaussians actually. Like every summation, where alpha and beta are just different eigenmodes, and in omega is there's a Gaussian center to the difference of the eigenmodes because it's causing that specific transition. Nothing weird about that. These gamma alphas are just the dephasing of this alpha and beta mode, which again includes both optically induced dephasing which will increase with the laser power, and the internal dissipation, which just exists in every system anyways. Now in this entire formula, almost everything is symmetric with alpha and beta, except for the top parts of the population. So transition from alpha to beta is proportional to the alpha population, and from beta to alpha will be proportional to beta population, right, in this way. So transition from lower to bottom will be different than top to bottom because of different populations in the two energy levels. And that is what we are kind of seeing in these plots as well, that at a lower optical heating, you have a significant population gap. So you see significant, these two peaks, which both corresponds to transitions. This one corresponds to transition from first to second, and this one corresponds to transition from second to first, and they are just different population. But if you increase optical laser heating, it kind of goes to the direction of this infinite temperature like heating, where the populations tend to equalize a bit. So the symmetry is quite large, and it's quite tunable with the laser power. That is all I wanted to say about the skyrmion project. So just as a summary, it took a skyrmion, assumed some light shining on it, and modeled the classical and quantum scattering. And we found out that, okay, there is a clear signature difference between classical and quantum, which appears in the second slide, is a sideband asymmetry in your optical output photons. And this asymmetry is quite large and tunable. Anyway, something I forgot to mention between this is not there's not a new idea which necessarily came up with. Something very analogous exists in optomechanics. And there it was indeed experimentally also probed, and that was one of the initial experiments to show that, yes, mechanics is showing quantum mechanical behavior. So it's something I should have mentioned in the beginning, I think, is the motivation. But yeah, it's a known phenomena which appears a lot in Brion light scattering. And before closing, I have one more slide as an advertisement. I have a PhD position. Okay, to be precise, I will have a PhD position when I join in this institute, IFIMAC, located in this amazing city of Madrid. So if you know any master's student who wants to come to Madrid, enjoy Spanish food, ask them to contact me. Thank you.